Hello and welcome to Studying with Chris, where I try my best to explain topics to help both you and me understand concepts. Today, we'll be going over adding and subtracting radicals. So, before we add and subtract radicals, let's learn what like terms are. So like terms are essentially values that have the same variable and the same power. So for instance, 3x would be a like term with 1 over 2x, since both their values have the same variable to the same power. Similarly, if we had 1 over 3y, it would be a like term with 4y. Now, this is also the same case if we add just numbers. So if we add 0.5, this would be a like term with 5. And additionally, if we had 2x squared, this would be a like term with 1 over 3x squared. Now, let's look at radicals. So, we can only subtract or add radicals if their indexes and radicands are equal and if their coefficients are like terms. So, for example, say we have root 48 plus root 75. Now, the radicands are not equal right now. However, we can convert them into mixed radicals in order to see if we are able to add or subtract them. So, 48 is divisible by 16 to make 3. We know that 16 is a perfect square, so we can factor this out as a 4, so we'd have 4 root 3. Now, we do the same thing with 75. 75 has factors of 3 and 25. 25 can be factored out to have 5 root 3. Now, both their indexes are equal, since both have the root of 2, their radicands are both equal, and their coefficients are both like terms. So, in order to add them, we simply just add the coefficients. So 4 plus 5 is 9, so our answer is 9 root 3. Now, let's take a look at the case if they were variables. Say we add root 18x subtracted by root 2x. Now, before we do anything, let's define our variable. We know that our radicand can't be negative if our index is even. So, in this case, we define our variable as having to be greater than or equal to 0, since if it were negative, the radicand would be negative, and we can't be dealing with imaginary numbers right now. So now that we've defined our variable, we notice that our radicands aren't equal right now, so let's convert our radical to a mixed radical to see if they are like terms. So we know 18 has factors of 2 and 9. We know that 9 is a perfect square. The square root is 3. So when we factor it out, we have 3 root 2x. And this can't be factored down, so we just have minus 2x. Now, both their indexes are equal of 2. Both their radicands are equal of 2x. And both their coefficients are like terms, with this one being 1 and this one being 3. So 3 minus 1, this will just give us 2 root 2x. Awesome. Now let's look at one more example. Say we have root 4x to the 5 minus root x to the 3. Now, once again, let's define our variables. You can see that in both cases, x has an exponent that is odd, which means that if x were negative, the value inside would also be negative, and that can't be true right now. So let's define x as being greater than or equal to 0. X belongs to real. So let's begin converting these entire radicals to mixed radicals. So we know that 4 is a perfect square, so we can factor it out as a 2. And we know that for both of these variables, since xn times xm is equal to xn plus m, that this x to the 5 can be converted into x squared times x squared times x, and this variable can be converted into x squared times x. Now, since we have two x squareds, we can bring these both out to the coefficient, so we have 2 times x squared root x minus, and since we have 1x squared here, we can bring this out, so we have x root x. Now, are we able to subtract these two terms? The answer is no, since even though our indexes are both the same of 2, and our radicands are both equal, our coefficients are not like terms. 2x squared cannot be subtracted by x, so therefore this cannot be further simplified, and we just have to leave it as this. So let's try these with problems. So remember, our rules are that indexes and radicands have to be equal. Our coefficients are like terms. So let's start by looking at this problem. If you'd like to try this on your own, just pause the video. Otherwise, we'll start working through it. So root 63 and root 16 are both entire radicals that look like they can be converted to mixed radicals. We have to be wary that we also have a root of 3 and a root of 2. So let's start by converting root 63 into a mixed radical. So 63 has the factors of 9 and 7, and we know that 9 is equal to 3 squared, so we can convert this into simply minus 3 root 7. Now, if we look at 16, we know 16 is comprised of 2 and 8, which can be further simplified to 2 and 4, and 2 and 2. So 16 is equivalent to 2 to the 4, or we could also say it's 2 to the 3 times 2. So since we are cube rooting it, we can take the 2 out. So we can simplify this into 2 cube root 2. Now, since these were already mixed radicals, we can just bring these both down. So we have 4 root 7 plus 3 cube root 2. Now, we know that we have some that are like terms and some that are not. So let's look at both of our square roots. We have one that has a root of 7, another that has a root of 7. So we can simplify these two together to make root 7. Now, we also have a cube root of 2 and a cube root of 2, so we simply add these two together. 3 plus 2, we have 5 cube root 2. Now, let's try on the problems if we have two variables. So, once again, if we have variables, let's begin by defining them. Right away, since we know that our indexes are odd, we know that both x and y have the possibility to be negative, and we wouldn't need to worry about principal square roots. So, for both x and y, we just define them as being real. Alright, now we can begin. So, let's begin by converting both of these into mixed radicals. We know that 8 is 2 and 4, and this can be further factored to 2 and 2. So we know 8 is essentially 2 cubed times x, and we know that this y can be factored down into y cubed times y to the cube root. Now, we'll just do the same thing here. 27 is 3 and 9. 9 can be factored to 3 and 3. So we have cube root of 3 cubed times x. This is the same case here where we can simplify this to y cubed times y. Now, we'll see that we have two perfect cubes, so we can bring these both out. So we have 2y cube root of xy plus, you can see this can also be taken out, and this, so we have 3y cube root xy. Now, both our indexes are the same, and both our radicands are the same, and our coefficients are both like terms since they both have the same variable, the same power, so we can simply add this to be 5y cube root xy. And for our last problem, let's take a look at this question. So, we know that we have a right angle triangle with side lengths 2 and 5, and we have a square on the hypotenuse of the triangle that has side lengths of 4. Now, this is not drawn to scale. So, using this, how do we find the perimeter to the exact value? Now, exact value just means we can't have decimals, so we have to leave it in either a root format or in a fractions. So let's try solving this problem. If you want to try to solve it yourself, just pause the video, and otherwise we will start. So our main challenge will be solving the hypotenuse. So we know how to find the length of the hypotenuse from Pythagorean theorem. We know that a squared plus b squared equals c squared. So we know the length of c is equal to the square root of a squared plus b squared. So we can just directly convert this into square root of 2 squared plus 5 squared, which we can simply write this as square root of 29. So we know the length of this is square root of 29. Now, we also know that all these sides are 4. So before we get into that, let's first calculate all the whole number sides that we know. So we know this side length is 2 and 5, so we can do 2 plus 5. We also know the side lengths of this box are 4, 4, and 4, so we can plus 3 times 4. And we know that the length of this will be root 29 minus this side length. So we know that the entirety of this line will be plus root 29 minus 4. Now, we can just simply add all these together. So we have 2 plus 5 plus, this will be 12, and we can simplify this just to root 29 minus 4. Okay, so now that we have this question, we could just plug into our calculator, or we could just say 2 plus 1, 3, 15. We could just say this is 15 plus root 29 is our perimeter. So we'll leave it as our exact value because we don't want to go into decimals. And if we leave it as exact value, we can keep our radical. That will be all for today for adding and subtracting radicals. If you have any questions, just leave a comment down below and I will try my best to answer it. Otherwise, thank you for studying with me.